Dear friends, welcome for the PowerPoint presentation of Physics for Class 12. In today's session, we will study about electromagnetic induction. The topics covered are magnetic flux, Faraday's law, motional EMF, inductors and inductance, mutual inductance, AC generators, summary and worked examples. Welcome you all once again. Please note down all the important points discussed during this session. In section 6.1, we will study about magnetic flux. Magnetic flux is the total number of magnetic flux lines passing through an area. It can also be defined as the product of area of the surface and the component of magnetic field normal to that surface. In the diagram shown, the rectangular part is the surface, area of the surface, and the blue lines are magnetic field. The angle between magnetic field and normal to the surface is theta. Here the inclined line A is the area of the surface, normal to the area of the surface, that is A is the normal to the plane of the surface. Mathematically it is given as integral d phi b is equal to integral b dot dA, where d phi b is the flux passing through a small elemental area dA. B is the magnetic field. Integrating, we get phi b is equal to integral b dot dA, that is equal to b dot A into n. N is the normal to the plane A. B is the magnetic field, where phi b is the magnetic flux, dA is the elementary area, B is the intensity of magnetic field. The integral is taken over the area. Theta is the angle between B, this is B, and this is N, normal to the plane. The SI unit of magnetic flux is Weber. 1 Weber is equal to 1 Tesla meter square. Therefore, we can also write phi by as this is the integral of v dot dA, that is nothing but dot product if you remove BA cos theta. Let it be equation 6.1. Flux phi is equal to, therefore, in terms of area, if you want to calculate, we can write it as number of turns. If n is the number of turns, total number of turns, then the area becomes n into A, and cos theta is as usual given in the previous equation. Therefore, flux phi can be written as NBA cos theta. The CGS unit of flux phi equals Maxwell, or 1 Weber is equal to 10 to the power of 4 Maxwell. Dimensions of phi are within big bracket m L square t to the power of minus 2 a to the power of minus 2. To calculate flux, the normal is always drawn outward. Please see here, the normal is drawn outward. So we will repeat once again the section 6.1. Magnetic flux is defined as the total number. It is a number of magnetic field lines passing through that area. This is the area. See here, some flux lines are passing through the area, some are not. So what we have to take here, the number of lines passing through this area. It can also be defined as the product of area of the surface and the component of the magnetic field normal to that surface. Here n hat is the normal, or this is shown as A here, surface. Mathematically, integral phi b is d phi b is equal to integral b dot dA, or after integrating we get integral d phi b is equal to phi b, that is equal to, again we have written right hand side same, and this is written as b dot A into normal vectorial normal to the A surface area. Therefore, we can write again trigonometrically phi b equals b into b dot A cos theta. Therefore, flux phi is equal to NBA cos theta. Flux can be changed either by varying field density. Please see this equation. Phi b is equal to b dot A cos theta. Here we can change phi by varying either b or area A or angle theta. So one of the three parameters or all the three matters, three variables put together, we can change flux. So flux can be changed by varying factor b or factor A or factor theta. We have calculated some of the values of phi, the direction of phi with respect to theta. Here please see this figure. Theta can be varied from 0 to 90 degrees. It can be in line with B or it can be perpendicular. Theta is positive when the angle theta is 0 to 90 degrees, it is positive. But when it is 0 degrees, then the flux is maximum. For values of theta between 90 degrees and 270 degrees, phi is negative. That is, beyond 90 degrees, it is 90 up to 270 degrees. Therefore, theta is equal to, when theta is 90, the value is 0. Between 270 and 90, again, phi is positive. At 270, it is 0. That is, at 90 and 270, the values of magnetic flux is 0. Faraday's law, Lenz's law and Fleming's right-hand rule. In section 6.2, we will study about Faraday's law, Lenz's law and Fleming's right-hand rule. Faraday's law of electromagnetic induction. According to Faraday, whenever the magnetic flux linked with an electric circuit changes, an EMF is induced in the circuit. This phenomenon is called electromagnetic induction. So this induced EMF is directly proportional to the negative rate of change of flux. That is, E is proportional to d phi b divided by dt, d phi b divided by dt. So eliminating the proportionality sign, we can write it as E is equal to minus d phi b by dt. The negative sign shows that the induced EMF opposes the cause of production. In case of a closely wound coil of N turns, change of flux associated with each turn is same. Therefore, expression for EMF is given by the equation E is equal to minus N d phi by dt. Here everything is same, only we have added N because number of turns in the coil are N. Lenz's law. Lenz's law states the direction of induced EMF. It states that the direction of induced EMF or induced current is always in such a way that it opposes the cause due to which it produced. So it gives the direction which opposes the cause of production of induced EMF. And the direction is given by Fleming's right hand rule. Please stretch your right hand in such a way that thumb is perpendicular to magnetic field and which both are perpendicular to the induced current. This status is shown in this figure on your right hand side. So here the right hand is stretched in such a way that the thumb, the forefinger and the middle finger, this is middle finger and this is forefinger and this is the thumb. So when you stretch it, M in such a way that they are perpendicular to each other, that is thumb is perpendicular to the forefinger and perpendicular to the central finger. So here in thumb represents the direction of motion, that is please here mark M is marked in red. So M indicates the direction of motion and F, the middle finger or forefinger, F of forefinger represents the direction of magnetic field, it as shown here, and the central finger represents the direction of induced current. So M is for motion, M of thumb is for motion, F of forefinger is for direction of magnetic field, and C of central finger is the direction of current. In section 6.3, we will study about motional EMF. Please see the figure given below, where a straight conductor PQRS of length L moving in a magnetic field of intensity B with a constant velocity. This is moving with a constant velocity. PQ is free to move so as to vary the distance x as shown in the figure, that is the flux density or magnetic flux intensity is shown by the into marks which is going into the plane of the paper, and PQRS is a conductor with a variable arm PQ which is moving with a velocity v as shown in the figure. The relationship between flux due to B is given by B into Lx as we have seen in the previous sections. Since x is changing, the changing flux induces an EMF given by the equation E is equal to minus d phi by dt. But phi is given by the relationship phi b is equal to B into L into x, where B is the magnetic field intensity and L is the length and x is the variable distance. Therefore, E is equal to minus of d into BLX by dt. Therefore, that becomes BL dx by dt. Please note this is L. This is L. BL dx by dt. Therefore, dx by dt we know it is a velocity, that is distance over time. That from the basics we know BLV. E is given by E is equal to BLV. Again I will explain. Dx by dt is equal to V, the velocity of the conductor, PQ. The induced EMF is called the motional EMF. Section 6.4 we will study about inductors and inductance. Inductors. An inductor is a device that can be used to produce a known magnetic field in a specified region. A current I is established through each of the n windings of an inductor. A magnetic flux phi b links those windings. Please see the figure. In the figure, an inductor is shown. It is nothing but a coil with n number of turns. So, it is a device which produces magnetic field in a specified region. A current I is established through a voltage source V which supplies a current I through n number of windings of the inductor. A magnetic flux phi b links those windings. Inductance. So, previously we studied about inductors. Inductors is a device. Inductance is the characteristics, the specification. The inductance L of the inductor is defined as L is equal to N phi by I. That is, inductance L is equal to number of turns into the flux divided by the current. This is the definition of inductance. The SI unit of inductance is Henry, H. It is symbol is H and unit is Henry. 1 Henry is equal to 1 Tesla meter square per ampere. Eddy currents. The induced circulating current in a solid metal due to change in magnetic flux is called eddy current. See, there is a metallic block. If a current is induced, EMF is induced in this solid block, a circulating currents within the solid block itself are produced. So, within the circulating current in this solid block is called the eddy current. Eddy currents are used in electric furnaces, speedometers of motor vehicles, electric brakes in trains and energy meters which we use as watt-hour meters in our houses. Self-induction. In section 6.5 we will study about the self-induction. Self-induction, whenever there is a change of current in a circuit, the magnetic field associated with the current also changes, due to which an EMF is induced in the coil. This phenomenon of producing the induced EMF due to change of current in the same circuit is called self-induction. The self-induced EMF acts to oppose the change that produces it. In self-induction, the change of flux is directly proportional to the change of current. That is, del phi is equal to del I. Or flux linkage through a coil of n turns is directly proportional to the current through the coil. It is given by the equation d phi is proportional to di, or it can be written as n phi is proportional to I. So, eliminating the proportionality sign, we can substitute it by a constant L. Therefore, d phi is equal to L di, or when we consider the total flux, N phi is equal to Li, where the constant of proportionality L is called the self-inductance. L is also called the coefficient of self-inductance. Therefore, N is equal to Ni from the previous equation. N phi is equal to N phi Li from this equation. We will recollect and rewrite here. When the current is varied, the flux linkage changes and EMF is induced. Therefore, when flux linkage is changing, that is N into d phi by dt is equal to L into di by dt, that is equal to E equals minus of N into d phi by dt. N is the number of turns. This induced EMF E is equal to minus L di by dt. The self-induced EMF always opposes the change, hence it is also called back EMF. Let us repeat the contents of this slide. Self-induction. Whenever there is a change of current in a circuit, the magnetic field associated with the current also changes, due to which an EMF is induced. The relationship between flux and current is given by d phi is equal to L di by dt, where d phi is the change in flux, L is the inductance and di is the change in current. That is, the change in current is due to the change in flux. Therefore, we can develop relationship N d phi by dt is equal to L into di by dt. Therefore, E is equal to N times d phi by dt, we are retaining as it is, equal to E is given by the equation equal to minus N d phi by dt. The induced EMF E is equal to minus L di by dt. The self-induced EMF always opposes the change, hence it is called the back EMF. Mutual induction. Please see the figure. Here there are two coils. One called primary coil on the left side and the second one on the right side is secondary coil. So, this is primary coil and this is secondary coil. And in the primary circuit, a battery is connected to the coil with a switch K. E is the battery or a source of EMF or a source, voltage source. The secondary coil is a galvanometer is connected to the secondary coil to detect any production of the current in the secondary circuit. Galvanometer detects the current. So, let us read it. When a current changes in the primary coil P, the magnetic field associated with this current changes the flux linkage in the second coil. As we know, due to self-inductance, a flux is produced here. This flux, because links with the secondary coil, yes, because of a closeness, this secondary is close to primary. Therefore, the flux produced here links with the secondary coil, and in secondary coil an EMF is induced in the second coil. The phenomena of producing induced EMF in the coil S, that is secondary coil, due to the change in the coil P is called mutual induction. That means the flux is originally produced in primary, it is linked to the secondary, and in secondary an EMF is induced. In mutual induction, change in magnetic flux linked with the circuit is directly proportional to the change of current in the nearby circuit. So, mutual induction is due to change in magnetic flux linked with the circuit is directly proportional to the change in current in the nearby circuit. Therefore, the flux in secondary coil d phi 2 is proportional to di, where d phi 2 is the flux in secondary and I1 is the change in current in the primary. Therefore, it can be written as d phi is equal to, that is eliminating the constant of proportionality and substituting by a constant m, the equation becomes d phi is equal to m into di, where m is the coefficient of mutual induction in Henrys. Here m, the constant is called m and called mutual induction and represented by a symbol m, and its unit is Henrys. Applying Faraday's law of induction. So, applying Faraday's law, induced EMF is equal to minus d phi by dt. Therefore, we can write E as minus m d phi by dt minus m di by dt, because flux is directly proportional to the current. Therefore, m is minus of E dt by di. If di by dt equals minus 1, then m is equal to E. That is, mutual induction is equal to electric field or induced EMF. The coefficient of mutual induction is defined as the induced EMF produced in a circuit due to the change in current in the nearby circuit at the rate of 1 ampere per second. That is, 1 ampere per second is di by dt. That is, di by dt is equal to minus 1. That is, the minus 1 indicates the change. If di by dt equals minus 1, then m is equal to E, and hence the definition of mutual induction, which is defined as the induced EMF produced in the circuit due to change in current in nearby circuit at the rate of 1 ampere per second. Therefore, we can write again using this equation E1 equals minus of di2 by dt, and E2 is the induced EMF in secondary coil. So, it is due to I1 in primary. Please note, E2 is equals minus m di1 by dt. I1 is the current in the primary. Here E1 is equal to minus m di2 by dt. di2 is the current in the secondary. M is the mutual inductance for the coil arrangement. Magnetic energy. For establishing a current in the circuit, work is to be done against the back EMF. This work is stored as the magnetic energy. For the current IE at an instant in a circuit, the rate of work done is dW by dt, work done per second. That is equal to E into I, that is electric intensity into the current. I is the current, but E is equal to Li, current through the coil, L into I, and that can be written as di by dt. L di by dt is the equals E. Therefore, total work done is the integral dW equals work done is equal to 0 to I till the current is built up I, Li di. Therefore, integrating we get integral dw is equal to w. I is taken out, I di, L is taken out, which is a constant. Therefore, integral dl I into di will be equal to I square by 2. Hence, the work done will be W is equal to half Li square. If an inductor carries a current I, the inductor's magnetic field stores an energy given by the equation UB is equal to half Li square. The value of W equals half Li square is nothing but the energy, and it is written as half Li square. This is the magnetic energy. Density of stored magnetic energy, it can also be written in terms of magnetic field intensity. Therefore, UB is equal to B square divided by 2 mu naught. We have coefficient of self-induction and mutual induction summarized in this text box to your right. Coefficient of self-induction. For a solenoid, the induction is given by mu naught n square pi into r square divided by L, where r is the radius of the solenoid, L is the length of solenoid, n is the number of turns, and mu naught is the permeability of air. If there is a straight wire, the value of inductance is L is equal to mu naught into R. R is the radius of the conductor or wire divided by 2. For a circular loop, L is equal to mu naught into N into pi into capital R, where capital R is the radius of the circle. N is the number of turns in this circular loop. Mu naught is the absolute permeability or permeability of air. The coefficient of mutual induction between two solenoids is given by the equation M is equal to mu naught N1 N2 into A divided by L. Please remember these formulae. The derivations are also given in standard textbooks. We are not covering this because to simplify our presentations. AC generator. In 6.8, we will study about AC generators. We have been using in our houses and shops a small AC generator. Let us see what it is, the working principle of a generator. The generator is shown in the figure to your right hand side. It has two magnetic poles, permanent magnet N and S. AC generator, in AC generator, mechanical energy is converted into electrical energy by virtue of electromagnetic induction. If a coil of N turns, this is a coil of N turns, it has got N turns, but in the figure only one turn is shown, and area of cross section A rotated at an angle omega. This is the angular velocity omega. This is rotated, this coil is rotated at the angular velocity of omega radians per second in uniform magnetic field. This uniform magnetic field is produced due to the permanent magnets N and S. The motional EMF produced is given by E is equal to NBA omega sin omega t, as we had derived earlier. Here we have assumed that at t equal to 0 seconds, the coil is perpendicular to the magnetic field. This is the magnetic field, direction of magnetic field, and coil is perpendicular. The direction of current changes periodically. The direction of periodically changes due to the motion of the coil. Therefore, the current is called alternating current. AC generator consists of a coil, a rotating coil. This is the rotating coil whose axis is perpendicular to the direction of a permanent magnet Ns. The rotation of coil by an external device, this is rotated by an external device, causes the magnetic flux to change. That is, the flux between N and S changes due to rotation of the magnetic coil, and EMF is induced in the coil. The ends of coils are connected. The ends of the coils are connected to a carbon brush through slip rings. Flux through N turns equals phi is equal to B dot A, where B is the magnetic field intensity and A is the area of the coil. Both are vectors. That is also given by the equation NBA cos theta, as we had studied in section 6.6 and 6.7. So this can be written as theta is equal to, in terms of angular velocity, can be written as omega t, because the angle itself is varying from 0 degrees to 90 degrees, 90 degrees to 180, 180 to 270, and again it comes back to 0, as we had shown in the table previously. Therefore, flux through N turns of the coil is given by NBA cos omega t. Therefore, induced EMF is given by the equation E is equal to d phi by dt. So, we will substitute the value of phi in this equation d phi by dt. Hence, it becomes d of phi, that is d of NBA cos omega t divided by dx. Therefore, NBA omega sin omega t. When sin omega t is equal to plus or minus 1, that is omega t is equal to 90 or 270 degrees, E is equal to maximum. Therefore, E will be equal to NBA omega, that is differential of cos omega t. It becomes omega, NBA omega. When sin omega t is equal to 0, we know sin 0 is 0. Therefore, E will be equal to 0. In general, we can write the equation as NBA is maximum, E maximum, therefore, E maximum into sin omega t. This equation E is equal to E max sin omega t can also be written in terms of current equation. Hence, the relationship between time and the current is shown in the graph, is graphically represented on the right hand side. Here, the current I is varying with respect to time. It is 0 when t is equal to 0 and maximum when 90 degrees. Then again it falls down, and at 180 degrees it becomes 0. See here, E equals 0 at when omega t or theta equals omega t is 0, maximum when 90 degrees, and again 180 degrees it becomes 0, and it becomes negative maximum at 270 degrees, and again after completion of one cycle at 0 it becomes 0. This is called sine. It varies cyclically as a sine function of t. That means current or voltage vary as a function of sine. sin omega t, and it is called a sine wave. Hence, AC voltages are generally sine waves. Symbols, units and dimensions. In section 6.9, we will study about symbols, units and dimensions. The first parameter is magnetic flux. It is represented by phi b and its unit is Weber. Its dimensions are ml square t to the power of minus 2 a to the power of minus 1. Its relationship with area and field intensity is phi b is equal to b dot a. EMF is represented induced. It is electromotive. It is called electromotive force. Its symbol is E. Sometimes we write as EMF or E, normal E. So we write E or E, and that is volt. Its unit is volt. Its dimensions are m L square t to the power of minus 3 a to the power of minus 1. The relationship between phi and EMF is given by E is equal to minus n of d phi by dt. Mutual inductance. Mutual inductance is represented by the symbol M, capital M, and its unit is Henry. Sometimes we write Henry as H. Therefore, the dimensions of mutual inductance are M L square t to the power of minus 2 a to the power of minus 2, and it is given by the equation E1 is equal to minus M12 into di2 by dt. Please note here E1 is the EMF induced in the coil 1, coil number 1, and change of current is taking place in coil number 2. That is why we are writing E1 is equal to di2 by dt, and constant mutual inductance is between coil 1 and 2. This is written in this form. Self-inductance. Self-inductance is represented by symbol L, and its unit is Henry, and its dimensions are m L square t to the power of minus 2 a to the power of minus 2, and it is given by the equation E is equal to minus of L di by dt. Now let us summarize whatever we have learned in section 6. The first point is magnetic flux is defined as BA cos theta, where theta is the angle between B and A. Faraday's law of electromagnetic induction implies that the induced EMF is directly proportional to negative rate of change of flux. Therefore, E is proportional to d phi by dt, where d phi by dt is the rate of change of flux. Eliminating the constant of proportionality or substituting the proportionality by a constant, we get E is equal to minus n d phi by dt, where n is the number of turns in the coil and d phi by dt is the rate of change of flux. Current I is written as I is equal to your E by R. R is the resistance of the circuit. Lenz's law. The direction of induced EMF or induced current is always in such a way that it opposes the cause due to which it is produced. Negative sign shows that induced EMF opposes the cause of production. Hence, it gives the direction of induced EMF. Motional EMF. When a metallic rod of length L moves in a magnetic field intensity P with a downward velocity V, an EMF, the induced EMF is given by E is equal to BLV, where V is the velocity. Please note here V is the velocity, L is the length. of the conductor, and B is the flux density or field intensity. Eddy currents. Changing magnetic fields can set up current loops in the neighboring metal bodies. They dissipate electrical energy as heat. Such currents are called eddy currents. That is, the changing magnetic fields are setting up current loops in the neighboring metal bodies. They dissipate electrical energy as heat. Such currents are eddy currents. Inductors. An inductor is a device that can be used to produce a known magnetic field in a specified region. The inductance L of an inductor is defined as L equals N phi by I, where N is the number of turns, phi is the flux, and I is the current passing through the coil. Mutual induction. The phenomenon of producing induced EMF in a coil due to change in current in the nearby coil is called mutual induction. Mutual induction is equal to minus of E dt by di, where M is the coefficient of mutual induction in Henrys. Thus, coefficient of mutual induction is defined as the induced EMF produced in a circuit due to change of current in the nearby circuit at the rate of 1 ampere per second. The self-induced EMF E is equal to minus of L di by dt. The self-induced EMF always opposes any change, increase or decrease. Hence, it is also called back EMF. Coefficient of self-induction of a solenoid is given by L is equal to mu into mu naught N square A into L, where mu naught is absolute permeability of air or vacuum and mu is the permeability of the medium. AC generator. AC generator converts mechanical energy into electrical energy due to the principle of electromagnetic induction. Therefore, E is given by E max sin omega t. Having summarized chapter number 6, we will take up some worked examples. Example 1. A solenoid with 15 turns per centimeter has a small loop of area 2 cm square placed inside the normal to the axis of solenoid. If the current carried by solenoid changes steadily from 2 amps to 4 amps in 0.1 second, what is the induced voltage in the loop while current is changing? Please read the question once again yourself and note down in your book. Solution. Given n is equal to 15 number of turns per centimeter. Please note it is number of turns per centimeter. This number of turns should be converted into number of turns per meter. If there are 15 turns per centimeter, therefore for 100 centimeters the number of turns will be n is equal to 15 into 100 equal to 1500 turns per meter. Area of cross section. Area of cross section is given as A is equal to 2 centimeter square. This also has to be converted into meter square. Therefore, this will be 2 into divided by 100 into 100. That will be 2 into 10 to the power of minus 4 meter square. Therefore, current is I1 is equal to 2 amps and I2 is equal to 4 amps. Therefore, dt is equal to, in 0.1 second, it is given that initial current is 2 amps and final current is 4 amps. in 0.1 second. The question asked is we have to find out the induced voltage E. We know the equation B1 is equal to mu naught NI1. Initial field magnetic field intensity is equal to mu naught N into I, and finally B2 is equal to mu naught N times I2. Therefore, d phi is equal to B2 minus B1 into A, that is equal to mu naught into N into I2 minus N1 into A, because phi is equal to B by A. So, here for knowing the value of phi, we have to multiply flux density with area. Therefore, substituting the values we get, mu naught is 4 pi into 10 to the power of minus 7, N is the number of turns 1500, I2 minus I1 is 4 minus 2 into A is 2 into 10 to the power of minus 4. That is equal to 7.6 into 10 to the power of minus 7 Webers. Therefore, we have calculated the value of B1. Now we have to find E, induced EMF E, which is given by the equation delta phi by delta t. That is equal to 7.6 into 10 to the power of minus 7 divided by 0.1, because current is changing in 0.1 second. This is given by 7.6 into 10 to the power of minus 6 volts. This is the answer. Let us take up example number 2. A rectangular loop of sides 8 centimeters and 2 centimeters with a small current is moving out of a region of uniform magnetic field of magnitude 0.3 Tesla, directed normal to the loop. What is the voltage developed across the cut if velocity of loop is 1 centimeter per second in a direction normal to the longer side when it is normal to the shorter side of the loop? For how long does the induced voltage last in each case? I will read the question once again. Please note carefully. Example number 2. A rectangular loop of side 8 centimeters and 2 centimeters with a small cut is moving out of a region of uniform magnetic field of magnitude 0.3 Tesla, directed normal to the loop. What is the voltage developed across the cut if velocity of loop is 1 centimeter per second in a direction, velocity is in a direction normal to the longer side, case 1, and case 2, it is normal to the short side of the loop. For how long does the induced voltage last in each case? Given loop of length 8 centimeters, that is converted into meters, 8 into 10 to the power of minus 2 meters. Breadth of the loop is 2 centimeters. B is equal to 2 centimeters, 2 into 10 to the power of minus 2 meters. And B is given as 0.3 Tesla. Velocity V equals 1 centimeter per second. That is equal to 10 to the power of minus 2 meters per second. We know the formula E is equal to BLV. So, here it is a straightforward substitution. 0.3 into 8 into 10 to the power of minus 2 into velocity is 10 to the power of minus 2. That is equal to 24 into 10 to the power of minus 4. Time for which induced EMF will last is dt is equal to distance over velocity. Therefore, that is equal to distance is 2 into 10 to the power of minus 2 divided by velocity is 10 to the power of minus 2, that is equal to 2 seconds. The conductor is moving outside the field normal to the shorter. Case number 2 is normal to the shorter side, that is B is equal to 2 into 10 to the power of minus 2. We know the equation is given by here, because it is moving through the breadth B, the equation becomes E is equal to B into capital B into small b. Small b is the width of the loop, smaller side of the loop, and V is the velocity. So, substituting the values, B is equal to 0.3. B is 0.3 into small b 2 centimeters, that is equal to 2 into 10 to the power of minus 2, and velocity is 10 to the power of minus 2, that is 1 centimeter per second is equal to 10 to the power of minus 2 meters per second. Therefore, E's value is 0.6 into 10 to the power of minus 4. Hence, we are also required to find how long does the induced voltage last in each case. So, when the distance travelled is 8 centimeters, T is given by distance or velocity, that is 8 into 10 to the power of minus 2 divided by velocity 10 to the power of minus 2. So, this value has come from here 8 centimeter, and this value has come from the velocity, this part, that is equal to 8 seconds. Let us take up example number 3. A 1 meter long conducting rod rotates with an angular frequency of 400 radians per second. So, omega is equal to 400 radians per second about an axis normal to the rod passing through it at one end. The other end is in contact with a circular metallic ring. A constant magnetic field of 0.5 Tesla parallel to the axis exists everywhere. Calculate the EMF between the center and the ring. Please read the sentence. Solution. Given L is equal to 1 meter, omega is equal to 400 radians per second, magnetic field density is B equals 0.5 T Tesla, E equals what? We know velocity is equal to V is equal to L into W, that is velocity is equal to angular velocity into the distance. Therefore, average linear velocity is 0 plus L omega divided by 2, that is initial velocity is 0, then it is final velocity divided by 2. It is given by LW by T. LW by 2, sorry. E is equal to BLV, that is equal to 0.5 into 1 into 1 into 400 divided by 2. Omega is 400 radians. So, E is the value of E is 100 watts. Example number 4. Current in a circuit falls from 5 amps to 0 amps, that is changing current from 5 to 0 in 0.1 second. If an average EMF 200 volts is induced, give an estimate of the self inductance of the coil. That means here we have to find out the self inductance given di by dt, and value of E is 200 watts. Solution. E is equal to 200 V, di is equal to 5 to 0, that is equal to 5, and dt is 0.1 second. Therefore, di by dt is equal to 5 by 0.5, that is equal to 50. di by dt is 50. We also know the equation mod EMF is equal to minus L di by dt, that is equal to L is equal to minus of E divided by di by dt. The entire di by dt is taken to the denominator. Numerator E remains same. Therefore, let us substitute the values. Therefore, E given voltage is 200 volts divided by Li by Ld, that is di by dt is equal to 50. So, denominator is 50. So, L, the value of L will be 4 henries. That is the answer. Let us solve example number 5. A circular coil of radius 8 centimeters and 20 turns rotates about its vertical diameter with an angular speed of 50 radians per second in a uniform magnetic field of magnitude 3 into 10 to the power of minus 2 Tesla. Obtain the maximum and average EMF induced in the coil. So, we have to find E maximum and E average. If the coil forms a closed loop of resistance 10 ohms, calculate the maximum value of current. So, he has given the resistance as 10 ohms and we have to find maximum voltage, induced EMF and current. Calculate the average power loss due to the heating in joules. Where does this power come from? These are the questions. So, please read the question once again. I will read for you. A circular coil of radius 8 centimeters and 20 turns rotates about its vertical diameter with an angular speed of 50 radians per second in a uniform magnetic field of magnitude 3 into 10 to the power of minus 2 Tesla. Obtain the maximum and average EMF induced in the coil. If the coil forms a closed loop of resistance 10 ohms, calculate the maximum value of current in the coil. Calculate the average power loss due to heating in joules. Where does this power come from is the question. Solution. First, we will calculate the flux. Flux through each turn is phi is given by phi is equal to B into A, vector B into A, that is also eliminating the vector sign and substituting by a dot product. We know phi is equal to BA cos theta, that is equal to theta is omega t, because it is theta is varying with angular velocity with respect to time. Therefore, for n turns phi is given by n b pi r square, because it is a circular coil with a radius r, the area of circle is pi r square cos omega t. Here we have just substituted the formula for area as pi r square. Therefore, induced EMF E is equal to d phi by dt. So, here we will substitute the value of phi as calculated in the previous equation as n b pi r square cos omega t divided by dx. That is equal to n b pi r square omega sin omega t, that is integrating differentiating this value, we get n b pi r square omega into sin omega t. Therefore, E maximum is equal to NB pi r square omega when it is 90 degrees. When omega t is 90 degrees, we get NB pi r square omega. Therefore, that is equal to 20 into 3 into 10 to the power of minus 2 into 3.14 into 8 divided by 100 into 50. That is equal to 0.603 volts. Average EMF over the cycle is 0 because there is a positive cycle and a negative cycle. So, average is 0 for any sine wave. Hence, here also average EMF is 0. So, current maximum is given by E max divided by R, that is equal to E max we have calculated as 0.603, substitute 0.603 divided by 10 ohms the given resistance, that is equal to 0.0603 amps. Power loss is given by half E maximum into I maximum, that is EI by 2, E max into I max by 2, that is equal to half into 0.603 into 0.0603, that is equal to 0.018. It is also given by I square R. This I is 0.0603 into 0.63 into R. The induced current causes a restoring torque in the coil. An external source, that is a rotor, is responsible for supplying the energy. So, in AC generator, the external source supplies the energy. With this, we have come to the conclusion of chapter number 6. Please go through the lecture of chapter number 6 again and again and note down all the important points. See you in the next session. Thank you.